Alright, hell yeah. So I'm taking the MIT Open Courseware Engineering Dynamics. And this is kind of the first problem. It's a kind of a refresher in kinematics. But it's not trivial. We have a football that's being kicked at some sort of angle. It has an upward component of the velocity and a component of the velocity that way. So this is kind of what the football would look like. It runs into some grandstands. And we want to know the height that it hits the grandstands, and because the grandstands are at a 45-degree angle, that's also how deep into the grandstands that football is going to land. And so we're going to use the kinematic equations. Now in this video, I go over how to solve them using an integration approach. So I think it's important to write what the definitions of acceleration is. That's going to be change in velocity, change in time, and the definition of velocity, that's going to be change in position, change in time. And for these problems, we know that the ball has mass, and so we know that gravity is going to affect that mass, especially if it's airborne, at a rate of negative 32 feet per second. So every second, this thing is going to be slowing down. If it has a velocity in that direction, it's going to be slowing down until it comes to a stop, and then it's going to have velocity in the negative direction. So this is the negative y, this is positive y, this is the positive x. And with the kinematic equations, we have to solve them in terms of two different components. You know, in the vertical direction is going to be different than the horizontal. So in the horizontal direction, the initial velocity is going to be the cosine of 60, which that's going to be 50% or 0.5 of this 80, so it's going to be 40 feet per second. That's the velocity in this direction. And so the acceleration due to, there is no acceleration in this x direction because we don't have any like mass of Earth over here or over here. So I typically like to start with the y direction because we have a lot more going on. It can maybe easier to see, hey, acceleration is gravity. We got negative 32.2. How we integrate is, we do that in the video. But just the fast way is just like, cool, we're going to take that and then we're going to add a t plus a constant. How you do that is like when t is equal to 0, well, we do have some sort of upward initial velocity. That's going to be 80 sine 60. And then we integrate again. This becomes t squared, and this halves. This just gets a t. And then also we have a constant of integration. When t is equal to 0, right, what's our position? Well, this is going to be the origin 0, 0. Cool. So those are our three equations in the y. Moving over to the x. See, for these kinematics, it's maybe not super obvious that the acceleration is 0, and then you have to start with that. And I even almost made the mistake. So when we integrate, we just pick up a constant. There is, like, velocity isn't a function of time in this direction, but we do have integration constant. That says when time is equal to 0, hey, velocity is 40. Actually, at any time, velocity is going to be 40, and that's what this represents. When we integrate, we're going to pick up a t, and we're going to have an equation for position as a function. In 1 second, we're going to be 40 feet that way because that's our velocity in that direction. At 2 seconds, we're going to be at 80 feet. Cool. So here's our equations. I just kind of made them simple. Like, obviously, this is acceleration in the x, velocity in the x, and position in the x. This is acceleration in the y, velocity in the y, and position in the y. These are also all functions of time. Position is a function of time. Velocity is a function of time. Cool. So this method is going to use the coordinate method where, hey, we want to know, and then in the video I said, if we have a projectile, we can figure out the time that it hits the ground because we have an equation in the y direction that says, hey, it's going to go up in the air. If we have some sort of time value here, hey, we might be up in the air. And then as time goes down, hey, this thing is going to travel in the down direction. And it doesn't know the grounds here. It could go a negative. Let's say this was on a plateau or a cliff. But at some point it's going to cross this axis again. So we can set this side equal to 0. And that's going to be, and we could solve for the time that that's going to happen. And because it's quadratic, that time is also, if we throw in 0 here, that's also going to be 0, but we're going to have two solutions, one there and one there. So I just bring up the issue, or the topic of if we choose this height as our y value, this equation says if we throw in h right here, the time associated with that, I mean, we can solve for the time that, oh, whoa, this almost threw me for a loop. So this is an equation of height. If I just pick some sort of height, you know what I mean, let's call it h prime. So I'm just going to say, hey, h prime is going to happen there, and if the grandstands aren't in the way, h prime is going to happen there. You know what I mean? So that's what this equation says. It says that if I throw in some value of h, I can figure out the time that's going to happen. Okay, but I do have a couple equations over here. So if I also say, like, yeah, I thought of a way to make it simple. So here, if I want to put in 55 feet here, I'm going to put in 55 in this side, and I can find the time that this football is going to be 55 feet in this direction. So that's going to be the time at 55 feet in the x direction. And what we do is we kind of talk about in the video how these are two separate equations. I mean, these are a function of time, but these do not represent, either one of these equations don't represent the actual path of the football. Because the actual path of the football is y is height, and then x is distance. So if I actually look at a side view of the football, this equation is y is a function of position squared, you know, something something x, and it's going to be it's going to be something something squared, probably negative because it's upside down. But we have equations that are like y is something something t. So we have y is something something t squared, and then x is something something t. So those are the equations that we have. So this gives us the ability to kind of pick points. So if we pick 55 in the x direction, we can find the time that the football is going to be right there. Cool. So let's see what happens over here at this coordinate. We can say that this coordinate's 55 plus h, so that's what we have here, and this coordinate's going to be h. So I can say my x coordinate, I can say, hey, this is going to be 55 plus h is equal to 40t. And then so I have an equation there. And then I'm going to come over here to my y equation, and I'm going to say h is going to be equal to all this. And then this is my equation there. And if you're just into, you know, figuring out, you know, a couple equations, couple unknowns, there you have it, and you have your solution. I mean, if you can get to 2 equations, 2 unknowns, and you're satisfied, hell yeah, check that box. And I don't do too much more for this video. All I do is just know that I want to solve for h, so then I have to solve one of these equations for t, if that makes sense. Sometimes it's like, what do I solve for? Hell yeah, solve the first equation for t, and the simpler one is always a good choice. And then this is going to be 55 plus h divided by 40. I simple it, this is 55 divided by 40, this is 1/40th h, and then I'm going to use this. Hell yeah. So then all I did is I'm going to use this value of t and shove it into this equation. So if I put it right there and there, then this equation just becomes things with h. And I even took one step further and just, let's get the h over here. Now we have 0 is equal to all of this. And so let's throw in this value. So we have negative 16. Here's my value for t, and I'm going to square it, plus 80 sine 60. Here's my value for t, throw it in right there, minus h. And then all I did was graph it and then find the value of h, and hell yeah, and I'm satisfied. Okay, so this video we do go over some of the integration. I get kind of frazzled because, man, I do make an error, and I don't know, you know what I mean? One of the commenters challenged me to, like, hey, maybe do things a different method, and man, like sometimes it's better just to do, you know, the methods that you feel comfortable with. But I'm open to do things a different way. That's why I'm doing this. I'm going to try to do this problem like 4 or 5 different ways. And actually, this method is one that I would probably stay away from. I'm more inclined to be like, oh, hell yeah, I see this. as a line, and I would still use my kinematic equations, but then I would, for this next part, I'm going to say, well, this is just y is equal to a slope of 1x minus 55 is when it's going to intercept this axis. And so hell yeah. Then I'm just going to take this kinematic equation, put it in there, and then put this kinematic equation and put it in there. But it's just so funny how that's identical to actually just picking a point. And like, it's so fascinating that I almost don't see that. But in that regard, if I use this as my equation and then throw these kinematic equations, this is my y equation, this is my x equation, put it into this function, then I solve for t. But then I know that's going to be the time that we hit the grandstands. And then I would use that time to then, throw into either of these equations and get my y value or my h value. I think the easier way would be just like, hey, just get your x value this direction and then subtract 55. H is what they wanted for the problem, and again, that was 63.77. Okay, so thanks for joining me on this one. There's more video, and hell yeah. Alright, hell yeah. So this is the MIT Open Courseware. That's Engineering Dynamics. This is the first problem. So this is just to kind of get you, it's supposed to be a review problem, work on your kinematics. It's not trivial because you're finding the equation for, using acceleration in two different directions. We have, because of gravity, we're going to have g is negative 10 meters per second squared. That's going to be down. But we don't have any acceleration sideways. If we do have some velocity sideways, it's just going to stay the same. We're going to neglect air resistance, so you can just imagine we're on a planet with no atmosphere. If a ball is going that way with a certain speed, it's going to stay that speed. So that's the first concept question. What's the magnitude of the horizontal component of the football's velocity at the top of the arc? And it's going to be, well, we need to figure out the horizontal component. We have a total velocity of 80. It's at an angle of 60. And we can see that this horizontal component is going to be the sun is, if this is the angle, here's the sine component, here's the cosine. So we have 80 cosine 60, and cosine 60 is 0.5. So we have 40 feet per second. That's going to be our component in that direction, and the answer would be B. Okay, hell yeah. So now we're going to try to do this kind of as fast as possible. There's no reason to go fast, just other than, keeps attention. This problem, you're going to have two components. You're going to have, you can treat velocity as a component in this direction and a component in the vertical direction. So we're going to start here and say this is the y direction, this is the x direction. Again, we have gravity. I'm going to say that's the acceleration in the y. That's going to be 10 meters per second per second. If you write it like this, you can kind of see, and we'll throw a negative on here. And then this is going to be a change in velocity of negative 10 meters per second every second. So we do have some vertical component of the velocity, and that is going to be 80 sine 60. Sine 60 is 0.866, so this 80 times cosine 60, 80 sine 60. This is going to be 69.28 meters per second. Cool. And so what this acceleration says is that every second this is going to be reduced by 10. And what the hell are we even saying? Like, I totally forgot that we're not even in, we're in feet per second, my bad. So this is feet per second. Acceleration is going to be negative 32.2 feet per second. Holy Toledo. All right. And then, so that is going to be the velocity in the y direction. And then you could say the velocity, and that's going to be the initial velocity. You can throw a kind of a knot on there. This just means that, hey, this is a velocity at a certain point, so this is only for that point. It's not an equation. So that's kind of the difference. This is not a velocity as a function of time, which we'll get to in a second. Okay, so the velocity component, the initial velocity component in the x direction is going to be 40. That's going to be 80 cosine 60. Okay, so what we use, the equations that we use, is that acceleration is change in velocity, change in time. And the other equation that we use is velocity is change in position, change in time. This is the definition of what acceleration is, and it's the definition of what velocity is. If you take some big chunks of time, so you're going to be like, okay, so over a bigger chunk of time, this is going to be my change in velocity. This equation is only accurate if acceleration is constant or if it's the average acceleration. Same thing here. And gravity is a constant. It's just, it doesn't change as long as you're close to the surface of the Earth. Cool. So we're going to use these two equations, and I guess we're going to write them in derivative form. We're going to say acceleration is, dv dt, and velocity is dx dt. All right, so we're going to have we're going to say this is the acceleration in the y, and that's going to equal negative 32.2. Okay, so this is also going to equal dv dt, and this is going to be the velocity in the y. Now, when we integrate this, it will give us a velocity equation as a function of time. So we separate variables, and we're going to have dvy, integrate that, is going to be negative 32.2 dt. Okay, so we're going to integrate both sides. We're going to get velocity in the y direction as a function of time. To integrate a constant, we're going to have negative 32.2 t. All right, and we do have plus some constant of integration. What this means is like, hey, if this is a function of time, it should work. And so usually you're going to set like time is equal to 0, so this term just becomes 0. But at time is equal to 0, we're going to have some velocity in the y direction. We're going to have, this side is going to be 80 sine 60. And so we're going to have 80 sine 60 is equal to 0 plus c. So this constant has to be 80 sine 60. So the velocity as a function of time is negative 32.2 t plus 80 sine 60 as a constant. And you can see this is the kinematic equation would just say, hey, velocity as a function of time is acceleration t plus velocity initial in that direction. So whatever direction this is, y or x, you know what I mean, that's going to be acceleration in the y direction or acceleration in the x. So booyah. Okay, so now we can say that this acceleration in the y is, and I should say that velocity can also be change in y, change in t. And so we're going to have dy dt. You know, it's just choosing a direction. So I'm just going to say, hey, I could either, my velocity could be in the x direction like a car, or it could be in the y direction like this football going up into the air. So we're going to say this equation for velocity is equal to dy dt. And now we can separate variables. So we're going to have dy is negative 32.2 t plus 80 sine 60. And then we'll have dt. We're going to integrate both sides. Now this will give us the function of y as a, it'll give us the equation of the height, the y position of this football, basically the height of this football as a function of time. When we integrate this, this is t to the 1. Power rule of integration says that goes t to the 1 plus 1 divided by 1 plus 1. So that's going to be t squared divided by 2. And so we're going to have negative 16.1 t squared plus 80 sine 60 t plus a constant. So let's write it in. I just don't want to write this twice. When time is equal to 0, what's our y position? I'm going to set the coordinate right there equal to 0. So cool. When I put 0 in for both of these t's, 0 squared, and then this is going to be 0, my position is going to be 0. So 0 is equal to 0 plus a constant. So that constant has to equal 0. All right, and so then here's our equation of our position. Here's our equation of our velocity. And then we're going to do that same process in the x direction. This was in the y direction, x direction. So we're going to have acceleration in the x. Now, is there any acceleration in the x? The way I think of it is the only thing that's generating this thing having this gravity, having this acceleration of gravity, is the fact that the Earth is underneath. And so this ball is basically wanting to have a force, an attractive force to the center of the Earth. Now, since we don't have an Earth over here or over here, there's no acceleration in this direction. Alright, so this acceleration is equal to 0, and you can write that same equation. Velocity of x, or the dv dt is equal to 0. We'll separate variables, so we'll still do that same process. So we'll have 0 dt, and then integrate. Integration of 0 is just going to generate a constant. So we have velocity as a function of time. This is going to be velocity in the x, is going to be a constant. Cool. So, and you could also think that this is like t to the 0. And so when I throw in a time of 0, I'm going to have 0 to the 0. That's going to be 1. Well, let's just say it's 1. And so my velocity, when time is equal to 0, is going to be 40 feet per second. But you can also say that, hey, this is an equation for velocity as a function of time. It's not a function of time. So my velocity is always going to be 40 feet per second. So this part of the integral is where you get this. Velocity is always constant in this direction. And so we have that velocity as a function of t is going to be, I'm just going to write 40. I'm not going to write 80 cosine, 80. This is 80 cosine 60. Cool. And then we know that this is dx dt. So we're going to separate variables. We're going to have dx, bring the dt up here as 40 dt, and integrate. And we're going to get x. This is going to be an equation for position as a function of time. We have integration of a constant. That's just going to be 40t plus a constant. And so at time is equal to 0, this is going to be 40 times 0 plus a constant. Our position is going to be 0. So our constant has to be 0. So cool. This is an equation for our position, and this is an equation for our velocity. All right, hell yeah. Okay, so these equations work for, these are just the general equations for a projectile. We could have said that, generically velocity is going to be acceleration times time plus velocity initial. And position is 1/2 acceleration time squared plus velocity initial t plus the initial position. So you can memorize the kinematic equations from the integration process. You know what I mean? Because we, to get velocity, we took that acceleration term, multiplied it by t, but then we had to add the initial velocity. Because when time is equal to 0, we're going to have some sort of initial velocity, and that's what that's going to be. Same thing for position. And then when we integrate, for sure, this acceleration is going to be acceleration divided by 2, so it's going to be 1/2 a. The t, this time term squares. The velocity term that we picked up over here gets a t, and then the constant gets added on, just in case we have a position. Sometimes your positions just always are going to be starting at the origin, but sometimes they're not. But this is the generic form. And so in our case, where acceleration was 0, in the x direction, we just throw a big goose egg in for a, and then we just have the initial velocity in the x direction as a function of time plus the initial position. That position is 0. So hell yeah. So the position equation in the x direction is just 40t. So that's kind of how you use the kinematic equations. But I swear, I would teach the kinematic equations from the integration perspective and then the derivative. Because, like, and the only reason I would do it that way is because it's just so easy to start with a constant and then start integrating, and you just have to memorize less things. Now, with this, though, is like, I'm going to try to get better. Because at the end of this video, I was like, well, I want to make another video on, like, hey, if I have acceleration, and acceleration is a function of time, and then why, when I integrate this, why do I get a velocity equation? Why can I get velocity as a function of time, and why does it look like that? And then when I integrate, why do I get a position equation as a function of time, and what would that look like? Does it look like this? Yeah, position is like 0. Well, no, my position equation as a function of time would be like this. Oh yeah, position as a function of time. Oh, that's so fascinating. Yeah, so I'm going to start at 0. We're going to go in the positive direction, and then we're going to start going in the negative direction. So that's what it's going to look like. But this, now... Oh, and my bad. And this would be like the y direction. So sorry. This is just height as a function of time. And so the thing that I'm going to do in the next part of this video, not in this video, is get an equation for the football as a, what would we want? We would want an equation for, we would want the height of the football as a function of its distance this way. You know what I mean? That would be the equation of this. If I have height right here as my y-axis, and then kind of the length of the field as my x-axis, like traditionally this equation, the path that you would see of the football into the stands would be y is some sort of function x. You know, y is equal to something something x, and it's probably going to be something something x squared. Where this equation right here is y is equal to something something t squared. So that's why this isn't a complete picture of what the football is doing. That's why we have 3 other graphs that say, hey, acceleration is 0. And then we have velocity is constant. And then we have position in the x is like this, is linear. Because my velocity is constant, every second I'm going to be another like foot this way. Or if I'm going 40 feet per second, every second I'm going to be at 40 feet. So I'm going to be here, I'm going to be here, here, here. That's going to be 3 seconds. So that's where you get this set of graphs. And this is the x position as a function of time. So if you wanted to have a position of this football as a function of time, where you would want to plot both of these at the same time. So you would say, hey, in 1 second, I'm going to be over here, but I'm going to be up here. And then in 2 seconds, I'm going to be over here, but I'm going to be right there. And then you would take a smaller chunks of time, and then you would plot all those points. Or you can just get an equation. But these 2 equations, this is position is something something time, and it's just linear. So this is 40t, x is equal to 40t. This equation is going to be this. 1/2 acceleration, t squared, plus initial velocity, t. Okay, so that's kind of a review of kinematics. Now this problem gets a little bit trickier. The simplest would be like, hey, like let's figure out the time that it's going to hit the ground. You know what I mean? And how would we do that? Well, we have an equation for this height as a function of time. And and so when time is equal to 0, hell yeah, we're 0. But then, you know, probably when time is equal to about 4 seconds, this side is negative and this side is positive, where, yeah, you're probably going to hit the ground again. And so that's what this equation says. It says you're going to start at 0, you're going to get up to some max height, and you're going to come back down. Now, an equation like this doesn't know where the ground is. So this equation will just go on, it's a polynomial, it'll go on to negative infinity. So keep that in mind. Some of these equations are only valid for what makes sense for the problem. Cool, so that's just the kind of the common, like you could solve the time when it impacts there. But we want to know, so So let's keep on that tune. I would say, hey, if I have this equation that's a function of time, if I throw in 0 here, I can find the time when the football impacts the ground again. Well, let's say I have these grandstands here. Like, wouldn't it be useful to find the time the football impacts the grandstands? Yes. And so that's this problem. That's what we're doing. We're trying to find when that happens. And I don't mind doing it a different way than I'm used to, because what I've just laid out is like, hey, we don't have this equation as a function of, we don't have height y as a function of distance here. If we did have that, then we could get this equation, y is equal to something something x squared, and then we could get an equation for these grandstands. And then we could just equate those two and find that location. But what I've just set out is, like with kinematics, I know that if I set this equal to 0, I can find the time that it's going to impact the ground. Well, let's do that same process where we want to find the time where it impacts the stadium. And so I'm going to rewrite the equations. So we have acceleration in the x is 0, velocity in the x is 40t, position, velocity in the x is 40, position is going to be 40t. Acceleration in the y is negative 32.2. We have velocity in the y is negative 32.2 plus 32.2 t plus the vertical component of the velocity. That's going to be 80 sine 60. And then we have the y position, and this is a function of time. All these are function of times. And it's going to be negative 16.1 t squared plus 80 sine 60 t. Okay, hell yeah. Yeah, this is so interesting because I so want to just know that I can find this equation. You know what I mean? I've already done problems like this where I'm just like, hell yeah, this is a line and I can find the equation of the line and then I can go from there. But we said that, hey, we have these two equations for position. They're both functions of time, and I want to find the time that it impacts here. So let's get those equations again. We have x as a function of time is 40t. And then we have y as a function of time is negative 16.1 t squared plus 80 sine 60 t. And so what is my x? So I'm just using the variables that are on the page, and I'm saying my x location. So I'm going to basically find the location of this with x and y. So my x term is going to be 50 plus h. 55 plus h. My y term is going to be h. So that's my coordinates for that position. So then over here, I can throw that in. I can say, hey, my x in the x is going to be 55 plus h is equal to 40t. And then over here in the y, I'm going to have h is equal to negative 16.1 t squared plus 80 sine 60 t. Cool. And this makes sense because when I'm at this height, if this is my projectile, when I'm at a height of h, this is going to be the time that happens. And then also when I'm at a distance of 55 plus h, that's going to be the time that I impact the grandstands. So this time value is going to be the same, you know what I mean? And you could even say, hey, this is like time in the x, time in the x, time in the y, time in the y. You don't have to do this. But now you can have a separate equation that says, yeah, sure, time in the x is the same thing as time in the y for both of these. So, cool. And all right, so now we have two equations, equation 1, equation 2, and yeah, and we have two unknowns. We don't know what h is, and we don't know what t is. All right, that was messing with me. I almost forgot like how to solve for a problem. And because I'm so eager to solve for time. I usually always want to do that, but we don't have to do that. Like obviously you could go down the route and solve for time, and how you would do that is like, well, over here I'm going to change these h. Anywhere where I see an h over here, I want this is something something time. And so I'm going to say, hey, what I'm going to say h is equal to 40t minus 55. And then over here I would go 40t minus 55. And then I would have, I would get all the terms on one side and then use the quadratic equation. But what we're going to do is we're going, like the problem says, hey, what is this h? That's all they really want to know. They want to know where this is going to hit the grandstands this way and that way. All right, so what we want to do is solve for t. So we're going to say t is equal to 55 divided by 40 plus h divided by 40. And now everywhere that we have a t, we're going to put this in. So let's do that. So over here we still have an h, so we're going to go h is equal to negative 16.1. We have t squared. So let's save ourselves some time and then just do t squared right here. You can imagine that this thing is squared. How I like to do squareds is, hey, let's just do this term squared. So we're going to go 55 squared divided by 40 squared plus this term squared. I'm going to have h squared and then divided by 50 squared. Cool. So that make our life any easier? And then, so yeah, let's just do this. So we're going to have, I guess I don't need to write this h. So this h is, or what do I need to do? Oh, I don't know what I was writing here. Yeah, so here's the equation. Oh, yeah, we want to solve for h. Yeah, no, oh, yeah, I was on the right path. But we have h is equal to, and now I'm going to FOIL this negative 16 in. So I'm going to have negative 16.1 55 squared divided by 40 squared, and then plus, or minus, or plus a negative 16.1 h squared divided by 50 squared. Cool. And now plus, I'm going to substitute this in for t. So I'm going to FOIL this in. So I'm going to have 55 divided by 40 times 80 sine 60 plus 80 divided by 50 sine 60h. Whew, that's brutal. Okay, so I have two values that. All right, hell yeah. So man, like I can't even stand this process, but yeah, let's just go back to here. I mean, I guess I don't like we were not even in terms of symbols anyway. That was one of the suggestions, just like, hey, you should probably start out with all symbols, but like even here we're just trying to use fractions, and it's kind of like maybe not necessary. I don't know. Like sometimes just to run, because let's say you're going to make mistakes. Sometimes it's good to just use decimals that aren't even rounded very well. So this is 55 divided by 40, or some, I don't know. Let's just say this is 1.375 plus 1 divided by 50 is 0.02h. I don't know, I just like using decimals. And then when we square this, oh, and I totally messed up anyway. Man, this is bumming me out. Because when we square this, I'm going to have a third term here. Okay, so we're going to have 1.375 squared. That's going to be 1.89. And then we're going to have this squared, which is 1 divided by 50 squared, which is 0.0004 h squared. And then I'm going to multiply these two together. 55 divided by 40 times 1 divided by 50 times 2, and I'm going to have plus 0.55h. Alright, so hell yeah. So this is going to be t squared. And yeah, it's interesting. I don't know, that comment really messed with me because it's challenging. Like when people challenge you and you're just like, well, you should do it this way, it's just like, well, I don't know. You know what I mean? Like, and then they said, like, you shouldn't use your calculator at all. But, yeah, it's fascinating. It is a crutch, but it can help you go, like, this is the messy part. And there is some, yeah, I should probably do this in terms of all letters. That would be fascinating. But you're still going to have the quadratic equation, and then you're just going to have a mess of letters as well. And so, yeah, so that's kind of fascinating. So, I mean, one way that we could, I mean, we basically have, this is our equation, and here's our t. We're going to shove it into here. So I don't freak out, let's just do this. Negative 16.1 t squared plus 80 sine 60 t minus h. And then everywhere where we have t, we're going to input this equation, this right here. And then hell yeah, and then I'm just going to graph it into my calculator. You know what I mean? Because like from here to get the answer is just a bunch of quadratic equation. And I actually despise the quadratic equation just because it's a mistake maker. It's so easy to make mistakes. So we're going to type this in. Our variable in my calculator has to be x. But we have x squared plus 80 sine 60. Yeah, I was about ready to freak out. Especially with comments that are challenging. You know what I mean? They're just like, hey, you should do it this way. And it's just like, yeah, I could give it a try. And then we have, see, and I'm even doing it wrong. You know what I mean? I'm totally freaking out. Negative 16.1. So this t is going to be this. It's 1.375 plus 0.02 h. Yeah. Hell yeah. And we're going to square that. All right, hell yeah. And comments are so interesting because, you know what I mean? There's so much like control issues there. You know what I mean? Where you have one person that's obviously going to read the comment, so sure, there's just no avoiding it. But then you have one person that's just like you're you know, putting your dominance out there, and it's just kind of fascinating. It's like cool, like make a joke at the end or something, so no one cares. Anyway, so hell yeah, yeah, because I'm getting kind of frazzled from that. All right, sine 60, and then we have this t here. It's going to be this again, 1.375 plus 0.02. X is my variable for h. And then we have minus x. Hell yeah, we're going to graph that. H is going to be way the hell out there. We already know it's going to be somewhere in like the 100 feet because this is part 2. We've already done this problem. So we're going to go on our window. We're going to get x, crank it up to 120, and then booyah, we should have that crossing. Hell yeah, and we do. And see, my whole style is like, hey, can you not make mistakes? Can you do things where I'm going to go for a value of 100 and we're going to go 0 left bound. Oof. Alright, there we go. 0 left bound and 0 right bound. Oh, this is my value of h. This isn't the total distance out here. I totally always make that mistake. So we have h is equal to 68 h is equal to 68.8. There you go. 68.8 feet. And I think we might have a little error here. I thought someone said this was like 64, approximately 64 feet. But who knows? That's why we do it multiple different ways to try to to try to get the answer. Alright, hell yeah. And my calculator will store that value of 68. We're going to add it to 55, and we get a total distance of 123. Now this seems a little bit high, so I'm going to probably be done with this video since I kind of freaked out. But we did it, and but yeah, it'd be nice to have a second, you know, like a second opinion. Oh, and I guess what we can do is we can use this value of h. You know, now that we have it in our calculator, it's going to be x, and we could solve for, since we have this, we can solve for time. So time is going to be 55 divided by 40 plus h divided by 50. So that's, I'm going to store that as alpha t, and then if we know the time, then we can put it into this equation and get our value for y. That's going to be negative 16.1 alpha t squared plus 80 sine 60 alpha t. Cool. So we're going to have this y component is going to be 68.76 is my height. And hell yeah. That's going to be what we solve for h. H is this, this, and this. Now my x component is going to be 40t. So we're going to go 40 alpha t. Cool. And then, oh, so this one is a little bit messed up. So I think I do have an error here. Yes, I do have an error here. Because if we did this minus x, this would only be 41. Okay, so let's find our error. Alright, hell yeah. So what we're going to do, kind of slow down and get our equations again. We have x is 40t, y negative 16.1 t squared. Yep, then we have positive 80 sine 60. Cool. T, and our x, our coordinates over here are 55 plus h, and then a height of h. So this is going to be xy. Alright, and then I'm just going to take a quick peek on like where we could have gone wrong. X is 55 plus h. So we wanted to solve for h. H is going to be 40t minus 55. Oh, well, we wanted to solve for t. So that's going to be 55 divided by 40 and then h divided by... Oh, so here's my error. This is h divided by 40. It's so dumb. Holy Toledo. I guess that's maybe the other reason why letters are good, because you're less likely to make errors like that. But okay. So we have... so we're going to throw this value in for x. 55 plus h is equal to 40t. And then we're going to solve for, and then obviously we can throw this value in for h right there, and then we'll have an equation, h is equal to all this. We're going to solve for t, and yeah, so t is equal to 55 plus h divided by 40. I probably should have just done this, but now 55 divided by 40 is going to be 1.375, and then 1 divided by 40 is going to be plus 0.025h. Okay, hell yeah. So now I can kind of do that same process where, and we can get this. We can say this is going to be 0 is equal to, and I can get this, this is h, so negative h over here, and I'll go negative 16.1, 1.375 plus 0.025h squared plus 80 sine 60, 1.375 plus 0.025h. T minus h. So that's what we have in our calculator. Close. We just need to change this. So we found our mistake. I think that's almost better. Like, my videos are good because like I make mistakes and find mistakes. and that's a good skill to have. Alright, sweet. So now I'm going to graph that. And this, hopefully, somebody was saying it was pretty close to 64. So I'm going to go value 64, 0, left bound, right bound. Okay, hell yeah. And we're 63.77 feet. And now let's check our answer. So we want to find the time value. So H is this. In my calculator is X, just the letter X. And so we're going to go 55 plus X divided by 40. That's going to be the time. I'm going to store that as T. And now I can double check my answer. So this is going to be 40T, and that's going to be 118. So minus 55, that's going to be H. Cool, so we have a check in this direction. In the Y direction, we should get a height of 63.77. So we're going to use this equation, negative 16.1 T squared plus 80 sine 60 alpha T. Alright, so we have a check on reality, and thank God we got the right answer. Sweet. So that's where it's going to hit the stands. And this solution was kind of interesting. I've actually never done that, where you're just like, oh, I have coordinates for this point. So that solution was like not using. The other way that's kind of cool is to like, hey, just come up with an equation for this line. So maybe I'll do that one in a new part. Alright, hell yeah. So thanks for joining me on this one, and guess what? That's a video.